All right, good morning. Let's continue with our exercise from the previous class. If you have not yet, please go ahead and launch your project 11. The one related to management zones that we started last class. So on my side, I don't have any of my previous variables saved on my environment, so I'm gonna have to rerun them. And we're just gonna very quickly go through what we did last class. So we are again on the same page, we review it, and then we'll continue with our clustering exercise. So I'm just gonna go ahead and load my packages, read the data. So again, this data here is the one that we have a, okay, there we go. So this data here is the one that we combine all the previous layers for terrain, variables, and also EC. And also the data related, the yield related variables as well, all in one object. So in my case, I have those same 4,046 rows that we've been talking about. We also brought in the boundary. So make sure you run those chunks that import data as you're progressing here. Then we talked about k-means and how we're going to use k-means to create management zones. So k-means, again, basically the way that it works is it randomly chooses the number of k that you choose for that run. So let's say if we choose k equals to 3, it's going to randomly sample 3 data points from your data set. And then it's going to, so those would be the 3 randomly assigned points. It's going to calculate the distance of all data points to all the 3 centers, and then assign each data point to the closest center as part of that cluster. After that first step, then it recalculates the center mean based on all the points that were assigned to that center, and it just keeps doing that iteratively until it converges, meaning that the centers don't change anymore. And so at that point, we say that k-means found a solution for the centers. So this is a unsupervised algorithm, meaning that we don't have a y variable. We're not trying to explain a variable with all the x variables. We're just saying, take all these x variables here and find clusters for me based on their similarities. And also we talked about the fact that k-means only works with numerical variables. So flow direction here, although it was interpreted as numerical, but it was really a categorical variable indicating the direction, the cardinal direction, so that we cannot use it. We also talked about some of the shortcomings of k-means. So I am introducing k-means because it is the most popular clustering algorithm. You're going to see a lot of use out of that. However, it has shortcomings. So for example, k-means works very well when you have circular clusters and you don't have outliers. But if you have oddly shaped clusters, or if you have elongated clusters or with outliers, k-means is not the best option. Some of the other options would be here, dbScan is one of them. Agglomerative clustering is also a good option here. And perhaps spectral clustering as well. So one of the things with k-means is that because it is unsupervised, meaning that it does not have the labels, right? It does not know how many management zones there is in this field, or even, what would be how they would be called if it's something related to yield or something related to something else. So it does not know what it's looking for. It just looks for groupings. Right. And the fact that it does that also means that it does not know by itself how many groups there are there. And maybe you don't know either. Maybe we as the researchers, or maybe as the users, we don't know either how many groups there are, or how many management zones there are in that field. So we talked about standardizing the data and also removing NAs. I guess I was jumping ahead of myself a little bit. So that's what we did in this chunk here. Make sure you run this chunk where we're dropping NAs, selecting only the variables we want to keep, and then scaling them as well. So then we need to tell, at least initially, we need to tell k-means how many groups we want to try out. And I think this is where we stopped last class, where we were asking k-means to start with 4 groups. So the number of centers here equals to 4. And then we also talked about the end start being equals to 10. This just is the number of times the k-means is going to run behind the scenes and give you one solution. This is important because that first step of k-means is random. So it randomly chooses the same number of observations as what you have for k from your data set. And because that is random, it could end up that maybe by random chance, if you just run once, if the n star was equal to 1, maybe by random chance, it happens that your 3 random observations are very close together and are not really exploring the whole range of the data. And that may end up finding a local solution of the clusters, but not a global solution, meaning that perhaps it gets stuck on one part of your data. It does not converge properly. So for us to avoid that randomness affecting our results, we have normally an n start that's at least 10. So k-means runs 10 times and then gives you one result that I believe is the average of the centers that it finds. So we ran this piece of code here. This is really, it's really interesting because a lot of times we talk about these techniques and it sounds like, oh, wow, I'm going to do management zone creation. That's it. This chunk here is what is doing that. Of course, we have a lot of things to consider, like the number of Ks and how to decide that. But really, this chunk here is what is, in essence, is creating the clusters for the management zones for us. So if we run this and we just print mod km, so there's going to be a lot of things here, and we talked a little bit about this, and I want to just walk us through some important steps of this print. So we ask for centers to be equal to 4. So centers is the number of k on k-means. So 4 clusters, and then it's given us the size already of those clusters, and this would be how many observations were classified under each one of the clusters 1 through 4. And then for each variable that you give k-means to use on your clustering algorithm, in our case, we gave it 4 variables, it finds a center of the cluster. So for cluster number 1, if you think of this in 4 dimensions, the center of cluster number 1 would be at a value of elevation, of standardized elevation in this case, of 0.48, of slope 1.777, of ECA of 1, and then ECA deep of 0.73. So imagine that you have this 4-dimensional space and each cluster has a center, right? Those are the coordinates, if you want to think of it that way, for the centers of each one of the clusters for each one of the variables that we gave k-means. And then it gives us this clustering vector, which is kind of actually annoying that it prints all this. But basically think of the top row here being the observation number, and the second row here being the cluster membership or the cluster assignment. So then we have this, again, observation number, cluster assignment, and so on. So if we scroll through all this nonsense, we get to this part here where it's telling us the within cluster sum of squares by cluster, which is this value here. And then it gives us this metric of the between sum of squares divided by the total sum of squares being equals to 60.8%. So what are we trying to do here? What is our goal here? Is that the between sum of squares. So imagine that would be, if you have 2 clusters, the between sum of squares should be large. No, I'm sorry, it should be small. So the between cluster sum of squares should be small, meaning that there's not a lot of variability between the clusters, but there's a lot of variability inside of the cluster, meaning that the cluster is really explaining a lot of variability within it, but it's not a lot of noise in between them. So that's the way we want to think about this. And so this value here, the larger this value is, the more we are explaining. And right now we ran k-means with k equals to 4. So we have 4 clusters, 4 management zones. Now, what do you think would happen with this number if we increase k, maybe to be equal to 5? What do you think would happen with this number of how much is being explained by each one of the clusters? Can you say that again?
Would it be like lower percentage?
So this number here, well, you know what? Let's go ahead and try actually. So let's go back to the code here and let's just change centers to 5. So we had 60.8% before. Now I just ran centers equals to 5. If I print this, now I have an extra cluster here. And if we just browse all the way to the bottom, so this number here increased, right? So we increased clusters from 4 to 5, and this increased from 60.8 to 66%. Now, similarly, if we decrease this number, let's decrease it to 3, and let's print it. Let's see what happens there. Decreased to 55.1%, right? So what happens here is that the larger number of clusters we have, the more variability we're going to be explaining when we do the between divided by the total. And so, well, I guess in my example on the text here, I was proposing that we ran with 10 clusters equals to 10. We can do that just to keep. So if I do 10 clusters here instead and check it, it's going to be a higher number there. So 77.6%. So, with that, so you would then, at least one of the ways we could interpret this is let's just have as many clusters as we can, because that is helping us to explain variability on this exercise and to higher levels. So the problem here is that every time that you are increasing the number of clusters, you're also increasing the complexity of that. So imagine that if you have a field, so here creating management zones, if we have a field that is indeed highly variable and would benefit from having 10 management zones, then great, maybe that would be a solution here. However, what if it's a field that has some spatial variability and could already benefit enough from just 2 clusters, so from just 2 management zones? Why would you add extra complexity to that field and give 10 zones when you only really needed 2 to do a good job there as far as separating variability? So there is this sweet spot of how many clusters you have. So you want to have enough clusters that characterize the major variability of that field, but not more than that. So you don't want it to be extremely complex. You don't want to have 20 management zones if you only need 2. Right? If you do need 20, then fine, you can have 20. But if you don't need 20, why would you have so many, right? Because that's going to add complexity to the management itself. So that brings us to the fact that we need to find now what is the best number of clusters. Yes?
I just want to make sure that I'm following. So when we have number of clusters, then it should explain variability more than the overall variability in the whole field. Is that right? Am I following correct?
Yeah, so you can think about this that so imagine the field that we've been looking into up until this point. So that field, we saw that it has variability across all the different variables, right? Spatial variability. And now what we are trying to find out is how many clusters do we need to explain most of that variability? Because really, if you think about it, to explain variability 100%, you would basically have to have each observation as its own cluster, right? So really, maybe let's think of the extremes here. So the extreme on one side is to have 1 cluster, which basically means the whole field is just a fixed management, which is what we do already, kind of, right? With conventional farming. The other end of that spectrum would be to have each cell being in their own cluster. So we would have 4,046 clusters in my case. None of those are the optimal solution, right? The optimal solution is somewhere in between having 1 and 4,000. And most likely what we want to find is especially a number that's on the lower side, that that explains most of that variability already, not all of it, but most of it in a way that simplifies management, but still gives you the opportunity of applying variable rate where needed, right? So we want to find clusters that are different, but at the same time, we don't want to make each cell their own cluster because that would be overkill, right? So this is what, and of course, for you to explain 100% of that variability, you're probably going to have 4,046 clusters, which doesn't make sense. So we're never going to have clusters that are just a few and still explains 100% of variability, right? We're probably going to be reaching, so it's kind of like with nitrogen response, right? So the more nitrogen rate you apply, you see your yield increasing until a point, and then it reaches like this plateau level. We want to find what is that plateau level, but instead of nitrogen rate is number of clusters, right? So we want to find that level that, yes, I can keep adding clusters and getting just a very small marginal gain of how much variability I'm explaining, but I don't want to go there. I want to stay within the level that I gain a lot of variability by just adding one cluster and another one and another one. So that's kind of what we're looking for here in this next step, is to find that best number of K that explains most of that variability before we start reaching a plateau of how much variability is explained by adding just one more cluster. Does that kind of make sense?
Yeah.
I think,
So like, up to this point, we are just making the clusters. We are not describing like you need to apply like -50 based on like 2 or 4 clusters, right? Because
right.
after we bring the like response variable like might be yield, then we can only define we need to use 2 or 4 zones.
Yeah, so here the approach we're doing right now is just using the field level variables as far as terrain and EC to create clusters. And the first step of that is to find how many clusters this field need. And so that's what we're going to do right now. After that step, then we want to validate those zones or those management zones, because just because you have, let's say, 4 zones there, just by looking at a map that has values going from 1 to 4, where each number is a zone, doesn't really tell you much. I mean, all you know is that they're different, but in which ways we don't know. So then we have to validate them to understand what is making them different. And then after that point, we can use what we learned from that part of the exercise to determine how, first off, which inputs we want to vary spatially based on the management zones, and then how much, right? So that decision is going to come after this exercise is finished. It's going to be the next exercise. But that is the goal, right? That's the goal, is to find zones of the field that are similar in some aspects, and then treat them separately as far as a rate of a given inputs. So that is where we're going here. Okay, so what I want to show you next is, so how do we determine the number of K, the best number of K for a given data set? In this case here, for a management zone data set. So there are some different techniques that we can use here to learn from the data itself. So the data is going to tell us how many Ks it requires, and there are a few different ways to do that. So the first one here I want to show you is a plot that is called the total error by the number of Ks. So if you want to start typing with me here, we're going to use a function called fvis_nb_clust. So it's coming from the Facto extra package that we installed at the beginning of this exercise. So this function here is basically this is what it's gonna do. It's basically gonna try a given number of Ks. So let's say if we tell it to try from 1 to 10, it's gonna try from 1 to 10, run all those clusters. For each one of those K that is being running individually, it's going to extract the total error coming from that number of clusters. And then in the end, it's going to give us a plot where we have number of Ks on the x-axis and total error on the y-axis. So this function here, the first thing is that it takes is a data set. So it's going to be all all underscore v underscore n. However, if we remember all vn, so already has all of our numerical variables, it's already standardized. We don't have any NAs, we already dropped NAs, but it still has the geometry. So we just need to drop the geometry. If you remember, we use a function, so we can just give a pipe. We use a function that's called st underscore drop underscore geometry. So we're just dropping the geometry on the fly here. We're not saving this action to an object. So it's not going to be reflected in any object. It's just on the fly here. So if I just run that part, this just becomes a tibble, so a data set without a geometry. Okay, so it has this function here has a few arguments that we want to change. Yeah.
That was supposed to run.
So what I ran was I just highlighted this and ran that. So just the all v pipe st drop geometry. Yeah, but I think that if you run, I don't know if this would run actually. Yeah, I don't think it would, because we still have to provide some arguments here. So the next argument that we want to change is called method. So method here can take a few different values. We're going to give the one that's called WSS, or within sum of squares. If you wanted to learn more about what methods, you can ask this function. You can just get the help of this function. You go on the documentation. It's going to have here, if you come to the arguments and look for method, it has here the silhouette is one of them, the WSS for the total within sum of the squares, and the gap stat for gap statistics. These are three very common methods for unsupervised algorithms to assess the best number of groups. So we're going to start off with the within sum of the squares method. It has an argument for k.max. So here is what is the maximum number of clusters you wanted to try? I want to set this to 10. It could be more if you think you need more, but I think 10 is going to be enough in our case. And then he has this function, this argument that's called fun cluster. So FUN uppercase and then cluster. So this is the clustering function that we want this algorithm to apply, because we are using k-means as our algorithm to begin with. We want to say here k-means, and you don't have to specify it doesn't have to be within quotation marks, but also it's not the function either. It's just the name like that. So if we run this, now it should work. It may take just a moment here because it is running, k-means with 10 different number of clusters. So this is what we see here. So again, what this is showing us is the total number of clusters going from 1 to 10 in this case, and 10 because we asked it to be a maximum of 10, and showing the total within sum of squares. So as we see here, the total within sum of squares is the largest when we have just one cluster, meaning that the whole field is treated as one thing only. And then as we add clusters, this number starts to decrease until it kind of reaches a plateau. So this method is also called the elbow method, because ideally you would see an elbow shape here, which we kind of see in our case. And the decision of what number of clusters to take is before you start reaching this plateau here. So I would say the plateau is probably happening maybe between, I don't know, 3 and 5 perhaps is where we see this plateau happening here. So having 3 to 5 management zones in this field is where we would aim for if we're using this metric. I want to show you here the other metric as well, the silhouette width metric. So for this one here, the only difference, I left you the code already, you don't have to change anything. The only thing I changed was the method. So I just changed that to S, which stands for the silhouette method. And you can go ahead and run it. And we have a similar approach where we have number of clusters on the x-axis and the average silhouette width on the y-axis. And here we're looking for the highest number of silhouette width that is associated with the number of clusters that it would recommend to us. So here it is recommending, it is already giving us a recommendation of the highest silhouette width that was obtained when we had K equals to 2. You can see here that, I mean, I guess perhaps you could interpret that your elbow starts at clusters 2. I thought was more like 3 to 5, but it is a visual assessment on the case of the total within sum of squares. In the case of average silhouette, is already giving you the maximum number there, which is 2. So this is a case where at least my interpretation from the first metric would be to use somewhere between 3 and 5 clusters. And on the second one here is telling us to use 2 clusters. So one thing that we can do here, so there are many, I'm just showing you a couple of metrics to run for deciding the number of clusters, but there are really many more metrics we could use. And one approach that we could do is what I'm showing you here, and I ask you not to run this because it's going to take a while to run, which is to run, so this function here, nbclust, is a function that is going to try number of clusters from 2 to 6 across, let's see here. I have the number somewhere. Across 26 different metrics. So we just tried 2 metrics. This function here is going to apply the same concept, but to using 26 different indices and give us a vote of what is the number of cluster that was the most voted across 26 indices. So that is a more robust way of doing this. It's just you're allowing a lot of these different metrics to provide your recommendation, and then whichever number of K was the most voted across all 26 indices, that would be the recommendation of this algorithm here. So again, I ask you not to run this in class because that will freeze your console for a moment. On my side, I think it took, I don't know, 7 minutes or something. But after class, if you want to try this, please go ahead and do try that. When I ran this on my side, the most voted number of clusters was 2 clusters. So 13 of those 26 indices voted number of clusters of 2. And so based on that, my decision would be to keep forward with 2 clusters. That would be, which is something that matches also the silhouette width recommendation that we saw here. All right, so this is how basically we would have selected the number of clusters or the number of management zones that this field requires. So if we have made this decision now, we'll keep going with 2 clusters. Let's just run a model again and just specify that number of clusters of 2. So if we start typing here with me, we're going to call again that function k-means. We're going to give again the data set all underscore v underscore n and pipe that into a st drop geometry. So we drop the geometry and it runs properly. If we don't drop the geometry here, the algorithm is not going to work. It's going to say, I don't know what this column here is. It's not going to give us any answers. So then we want to say centers equals to 2 because that was our final decision. And then we want to say again, n start equals to 10, just so we allow it to run 10 times and give us the best answer. So if you just run that and you print it, now it's telling us that we have 2 clusters and these are how many observations each one of them have. This is, sometimes you may run clusters that maybe some of the clusters have very few observations in relation to the others. So maybe let's say if we had 10 clusters, maybe one of them would have like, I don't know, 10 observations. So this, of course, will only have 2 clusters, but I'm kind of glad that it's almost evenly split here, the number of observations in different clusters, because that gives us, I guess it's a better indication of being, evenly distributed data across both the clusters. So then we get the cluster means for all the variables we provided as well. Remember, these variables here were all standardized, so that's why we see those numbers like that. If we come to the bottom of this print here, you're gonna see again, our total sum of squares is just 40.6%, or the R between divided by total is just 40.6%. But these clusters were the most efficient across many different indices that we used. Okay, so this object, the object that we created, the mod, let's see, what was the name again? Mod KM2, it has the cluster membership, right? So we just went through all this, which for each observation now, this object mod KM2 has the membership being either number 1 or number 2 for each one of the observations, which relate back to what cluster they belong. So what we want to do now is we want to explore these clusters in the sense of I want to make plots, I want to make maps, I want to see how these clusters are in space, and we want to validate them with the other variables, meaning that we need to have a column in our data set that has the cluster ID so we can refer to. So let's go ahead and do that next here. So my goal is to create this object called ZoneDF, where we're going to start off with all underscore V underscore N. Give it a pipe, and if you come right after that comment, my goal right here, so if we just print all VN, it has those, in my case, 3,723 rows, and I have elevation, slope, ECA, deep and shallow, and the geometry. So my goal is to add a column here that's going to tell me what is the cluster membership of each one of these rows in my data set. So for us to do that, you just come after that comment. Let's give it a mutate. I want to call this column here as a cluster. So that's going to be the name of the column that we're going to bring here. And if we just call the object that we ran the k-means, so that is the mod, let's see, mod underscore KM2. If you use the $sign there, it has a whole bunch of options that we can choose from. And if we choose the cluster, I can just run this by itself so you see what that is. This is a vector with all the cluster membership for all observations. So if we just run this and we print ZoneDF, now we have the same number of rows as before. And if you go to if you just browse here to the left, now you have a cluster ID column in this data set. One thing that I want to change about it is what you see right now is that it is considered as an integer. And really, this is not an integer, right? It's really just a class. If I name them A, B, or something else like that, it would have the same meaning. Like here, cluster 2 is not 2 times larger than cluster 1. That it doesn't have a numerical meaning, it's by itself. So I do want to create a categorical variable out of that. So still within this same mutate, you just add a comma and break code. We're gonna call again the same name of the column. So it's still just calling cluster. So we're going to overwrite this column. And I just want to use the function called factor cluster. So this way I am forcing that column to be interpreted as a categorical variable rather than numerical. So if we run that and you print it, you're going to see now that we have the cluster column being interpreted as a factor or categorical, which is what we wanted. All right, so we have already seen a little bit of this. So how many observations there is in each one of the clusters. We've seen on the output of that object mod KM2. But what if I wanted to see that myself using, dplyr or some wrangling functions here? So again, my goal here being, I want to know how many observations I have in each one of the clusters by using some other functions from dplyr. How would you do this? Niva, any thoughts? No problem. Send us. Distinct, okay. So distinct. Let's see, distinct here would tell us the. It basically tell us, so let's say if we do distinct of cluster is gonna just return two, because it's gonna be just like two values. So it's something else. Ujwal, what do you think? So my goal here is to identify how many observations I have in each one of the clusters. So say that again, add-ins, what do you mean? Oh, a range. Okay, so I mean, we can try, right? The cool thing about programming is you can try, then it's not gonna hurt. So let's try first what Sandesh was saying. So if I do a distinct, let's say I do a distinct on the cluster, it's gonna return just those two numbers. This is almost like the output of what we want to have. It's just we want to have another column here saying n, and then how many observations we have. So distinct is not itself what we need, but it's kind of going the right direction. If we do a range, as Ujwal was saying, we're just going to arrange the rows, right? But we're still not sure. I guess you could come here and just count, which I guess is not what I want to teach you all, because this is not very efficient, but you could come here and just see where you switch from 1 to 2, I guess. So a range could be a possibility, not the most efficient one. Brunelisa, what do you think? Okay, so you're in the right direction. So a summary would help. Yes, okay, so Gonzalo nailed this. So he said we need to group by cluster and then do a summarize with n equals to length of cluster. That's exactly it. So let's go ahead and do that. Thanks, Gonzalo. So if you come here and we do, so every time we think of like, I want some type of summary out of different groups, and those groups are levels in a column, always think about group by. You need to first create that grouping and then extract something from it. So let's do here a group by cluster, which is the name of our column. And then I'm going to delete the range here so we don't get confused. And then we can do a summarize, where we can just say, I'm just going to call this n. So n is going to be the length of, I mean, we can even say length of cluster. So what is going to do? So the inside of length here could really be any column. It doesn't matter which one. The key is that we're getting the length of any of these columns, and the length just returns to you the number of rows within that column, but by each one of the groups that it finds on the group by. So this would be the answer for that. So if you run this, you would find that we have, again, 1,665 observations in cluster 1 and 2,058 in cluster 2 in my case. I do want to show you all a trick here, which I use a lot. And I think if you also program in Python, this may sound familiar. So one short version of this specific. So if you're asking for a summarize that you want to get the number of rows for different groups, this works perfectly. But there is a short version of that, which is just to ask for a tally. So the tally here does the exact same thing as this summarize, but it is a little bit shorter, perhaps easier to remember. But in the case of a summarize that is using the function length, that is exactly what tally is doing for us. So just wanted to show you all that shortened version as well. Okay. So now my next goal here is going to be to create a map of these clusters. And now I want you all to help me here to think of how we can do this. So I will tell you that I'm starting with that object, so zone df. I'm going to already call a ggplot here. And then now I want you all to help me to figure out the code here. So again, I want a map, right? So I want I want to show a map where each one of the pixels should have the cluster ID, so either 1 or 2, and I want to color those different cluster IDs differently as well. So what geom do we need here, Doug? GeoMSF, right? Because zone DF is an SF object, so GeoMSF. All right, so if we just do this, this is what we get. Now, how do I color each one of these cells or fill each one of these cells according to the cluster ID or the cluster column? AES, right? So we call AES here. And then, so just to print zone DF here to remind us the columns we have. So we would say, so we can say either fill or color, but I do want to say fill equals to cluster. So if we run that, this is what we get. And just a heads up on your side, perhaps you're getting, well, I guess a couple of things to note here. First one is, even if you had the same exact data as I have, which you don't, because again, our boundaries were different, grids were different, and so on. Even if you had the same exact data as I had, your colors may have been flipped. Because again, due to the randomness of the first step and the way that the algorithm works, it may call, in my case, cluster 1, the one on the right, and cluster 2, the one on the left. And in your case, it may call the opposite way. That could happen. And then compounded on top of that, you also have slightly different data because of the boundaries and the grid and so on. But overall, you should still see something similar. Like it should not be completely different. Yes.
So our numbers, like cluster 1 is the same color, cluster 2 is the same color, but the maps.
The map, like the in play, like in space, they're just flipped.
Yes.
Yeah.
Like your cluster, what's shown on yours is cluster 1 is shown on mine is cluster 2.
Okay, so do you mean that like you have the blue on this side and the red on that side?
And
Yeah.
our labels are the same.
Okay. Yeah, and that is completely okay. And this is something that whenever we get to the end of this exercise, you will have to really pay attention because so right now, you know, this is the first step of us showing in space where the clusters are. We're still going to do some processing on the cluster. So the immediate next step is going to be to clear up some of these speckles that we see. And then we will give meaning to these clusters. So we're going to run some models and understand what is cluster 1 and what is cluster 2 in relation to the variables that created those clusters. So we want to give meaning to them. So we want to say, well, cluster 1 here, you know, has a lower elevation, higher slope. The same way that we did for the previous exercise, we want to give context to these clusters in a way that in the end, we want to call them something. They're not going to be just called 1 and 2. They're going to be called perhaps high yielding, low yielding, or something like that, where we give context based on the variables and also based on yield data. So whenever we get to that point, maybe for me, my cluster 1 is going to be low yielding and cluster 2 is going to be high yielding. And maybe for you, it's going to be the opposite. In space, they're still the same, but just the way that 1 and 2 were named by k-means creates that difference there. So when we get to that point, I will remind you all of this difference here. Okay, so one thing I want to notice here, which I think is really interesting, is the fact that we did not provide geospatial coordinates to k-means. K-means was completely unaware of where if a given row in the data frame was neighboring or not neighboring another row in that data set. So the fact that when we plot this, we still see some grouping in space, I think is interesting for us to think about it as well. So really we can still see some spatial grouping of these or separation of these two clusters, mostly because of the inherent spatial variability that exists from the variables that we measure. Even though we did not explicitly say this is neighboring to that, but because these variables are correlated in space anyways, because we would expect that, you know, a part of the field that is closest to a given cell is going to be more correlated to that cell than a part of the field that's farther away from that cell. that is something that we do expect with geospatial data. So it's just the intrinsic dependence that exists on the data itself. It makes it in a way that our clusters are still somewhat cohesive in space and not just a random, mix of red and blue in this case. Right, so I think that is something interesting to notice. Okay, so I do wanna, so this plot in specific, I do wanna make some more customizations on it because you're gonna have to do some work at some point looking at this plot, and I want it to be easier for you when it gets to that point. So what I want to do here as well is first come back to GeoMSF and remove the black outline because it's really just adding noise there. So if you go outside of the AES, we just say color equals NA. In the case of polygons, color refers to the outline color and fill refers to the inside color. So by just removing the color of the outline, it just a little bit more crisp to see the actual differences. The next thing is I want to change this color scale to a colorblind safe scale. So add a plus, let's call scale underscore fill underscore colorblind. So we've been using Viridi's up until this point. I do want to show you a different one that's called colorblind here. So if you just run that, you should get something that looks like this. The next thing is I want to add the boundary. So let's add a plus geom underscore SF because the boundary is an SF object. We need to say data equals to, and the object is called boundary underscore W. And if we just run like this, the boundary is going to cover the data, which we don't want. So we just come to back to the boundary and say fill equals to NA. So we don't have a fill, we just have a color. So we just have the outline of the boundary, but no fill, so we can see through. The next thing is I want to add a title. So let's add a plus. To add a title, we're going to use the labs function. It has an argument that says title, and we're just going to give it the name unsmoothed zones. So if you run that, we have a title now, unsmoothed zones. I want to call the theme map, which is a theme, I think it's part of either ggplot or SF. Let's see, theme underscore map. No, it's actually part of ggthemes package, just to make it a little bit more clean and like to the point. And then lastly, I just want to change I just want to change the color of the title that we have of the plot. So I want the smooth zones to have a different color. I don't think we've done in this class a lot of customizations of the plot when it comes to those aspects. So this would be one way, I guess, one exposure to how you would do that. So let's add a plus. So to give a title, we use the labs function, but to customize something about it. So either the size, the color, the font type, the alignment, all those things would be under the theme function, theme by itself. So here, if you just hit tab, there's a whole bunch of arguments you can change. So a lot of these things you can customize in your plots. What we want to change here is something called plot.title. And when you are inside theme, most of the things that you are going to be editing are either text, a line, a rectangle. I think those are the main categories. In a way that I cannot just come here and say color equals to blue. It would not work like that. But what you have to do is first call a function that relates to the type of element you are editing. So plot title is an element of type text. So if you start typing element, you're going to see here, there's an option for blank, grub, line, rect, render, in text. You want the text one. And then inside of this function element text is where you can change a whole bunch of things about this title. So what I want to change is just to say color equals to blue, like that. So if you run it, this is what you should be seeing now, or something at least similar to that. Of course, maybe your colors may be flipped and your cells may be a little bit different again because of the differences in boundary, but overall, you should, if you are not seeing like this field somewhat split in the middle with a cluster to the right, a cluster to the left, then I would not expect that to happen. So if you're seeing maybe a cluster to the north and one to the south, maybe something happened in along the way. All right, so one of the things I want to point out here is, so each one of our cells, do you all remember what is the size of each one of the cells? 10 by 10 meters, right? Because that was the size of the cell, the grid, when we created the grid. So each cell here is 10 by 10 meters, which depending on the equipment that you may be using to apply something in a variable rate, it may be either, you know, smaller than a swath of that equipment, or it may just not be feasible for you to change a rate here. So have a rate where you are, and then 10 meters away, you have a second rate, and then another 10 meters, you have back to the first rate. So there is this speckling effect that we see here, where, for example, right there, right, you have a black, so for me, a cluster 1 surrounded by cluster 2. It may not make sense for that grower to really have this happening. Like we may want to smooth out this cluster before we actually use for anything else, right? Because we have these peckles that we want to remove to some extent to make things more, more smooth, I guess. Before we do that, I just realized that I forgot to ask us to save this plot to file. So before we move to the smoothing part of the exercise, let's just come back here and do a ggSave. So I want to export this to file because you will have to bring this into an assignment. So I want you to have this on file. So let's give it the path here, // to get outside of the code folder. Hit tab, select the output folder because now we're exporting a figure. I want to call this zones.png. And I want to change the width to be 3 inches and the height to be 4 inches. So if you run that and then you come over to your files tab and you go to the RBLU button and the output folder, you should have this map right there at this point. So one thing I want to show you as well, if you, on my side here, my laptop uses a dark theme, which is interacting with the way that theme map works. So theme map basically tells to have a transparent background on the plots. And because on my computer, I have a dark theme, this is how it looks like. Maybe if your computer is using a light theme, you may be seeing a white background. It's not my case. So for me, this is, you know, a lot of times, this is not ideal for, in my case, that I have a dark theme on my laptop. So if I want to force to not be a transparent background, but actually have a white background, one of the ways you can do that is on ggSave. It has this argument for BG, which stands for background, and I can say BG equals to white if I want a white background. So that solves the issue for me. And again, that is something that happens because theme map, which we're using here, is setting that background to be transparent. If you use a different theme, maybe you would not have that issue. But this is just how I would fix that if also was happening on your side. All right, so we have this unsmoothed map already. Now, I want to show you how we would smooth these zones. So make these zones more consistent, more cohesive, and not have all these speckles of one zone inside of the other. So we're gonna use a focal window. What is a focal window? So a focal window is you can kind of think of it as a matrix that we determine the size of that matrix. So in this case, this matrix here is a 3 by 3 size matrix focal window that it moves in space. So imagine that what it's doing here is gonna consider all these neighboring cells and take a function. That function could be the mean of all those cells, could be the minimum, the maximum, could be any summary function. In this case here, I believe it's taking the minimum. So what it does is for the pixel in the middle, it's considering all the cells that are within the focal window, and it is extracting the minimum value. In this case, the minimum value of all these neighboring pixels is 0, and assigning that value to this pixel in the middle, which is resulting in this. And then it moves one column to the right, does the same thing. So then when it moves to the right, so imagine that this whole window is moving one column to the right. Now the cell in the center would be 9. And then all the neighbors, it would not consider then the first column here anymore, but it would include the second column. And then it looks for the minimum value again. So imagine it would be starting here and stopping here. And the minimum value within what I'm drawing now is 2. So then the cell in the center becomes that. So I guess the concept here is that you have a size that can change. So this is a 3x3. It could be a 5x5, 7x7. You normally want an odd number because an odd number is going to have a center cell. If you have an even number, so imagine if you have a 2x2, you don't have a center cell, or a 4x4, there is no center cell. So odd number focal window sizes gives you a center cell right in the middle, and then you are considering all the neighboring cells inside of the focal window, and then you extract some information from that. In this example, here's the minimum value, and assign that value to the pixel in the center. So by doing that and just moving this window all the way to the right, and when it reaches the end, it goes to the bottom. So it's just a window that is moving in space and applying this filter, in this case, not a filter, but this function of minimum, creating this map. So in the end, we have something that looks like this, where, so we don't have cells on the border because those cells there, or we don't have values for the cells on the border because those cells don't have all neighboring cells. So they could calculate that, but we do have a new version of that, of this previous map, which is now a smooth version. And it is smooth because it is considering a lot of data to kind of give you one value, right? So imagine if this was the mean instead, it would actually be taking the mean of all those neighboring pixels and assigning that mean to the value in the middle, which in the end, the output of that map is going to be something that's more smooth, right? You don't have these abrupt changes. It's something that it kind of helps you to have more continuity, I guess. So our goal here is to apply this concept to this map with the intention of removing some of these speckles here. So imagine that whenever, so on this case, on my case here, if that black pixel that I'm kind of circling right now is in the middle of this focal window and all the neighbors are another zone, is going to turn that black one into yellow. So it's going to smooth out for us. That is the goal that we have here next. All right, so we're going to have to use a grid again. So because we've done this a lot of times, I'm not asking you to code that, but this is the same code that we used in the past to create the grid. So we're bringing the library stars to work with rasters. And then we're creating this object here called grid_r. Starting with the boundary, making a grid of cell size of 10 meters, turning that into an SF object, rasterizing it, and then cropping to the boundary of the field. So we've done this before already. You know, let me see something here. I think that maybe this is a good point for us to take a quick break. So we're going to 11:10 today. We're kind of half through there. So let's take a 5-minute break, and then we'll come back here so we start doing the smoothing of this layer. I'm going to put 5 minutes here, so that's going to be about 10:15 when we come back.
So my, the soils data is in 30 meter and my elevation is 3. Would it be easier to like make my elevation data 30 meter? That's what I thought about whenever you said that, was that I feel like it'd be easier to do that than make the other, break it in.
So I think it's gonna be like the ease of that is gonna be the same. It's just, so the way that I would approach that is using a ST join. So if you remember, we did the ST joins in the class before. I think you're gonna have to have a different join type. So if you remember, let me show you here. So when we use ST join, let me see if I even have that in this. No. So when we use ST join in our exercises, because everything was already matching,
We just get on the left.
yeah, so we did left equals true, which is what you want. But then we also, so if you see here, the default of the join type is ST intersects. For our case, that did not give what we wanted. And the way that we found that out is you look at how many rows the first data set has, you look how many rows the second one has. So let's say the elevation one is gonna have a lot more data points than the soils, right? And then you think, if you make the decision that you want to match so you want to basically break down the big soil pixels into smaller pixels that match the elevation, you have to start off with elevation, do an ST join, and then call your soils data. And you would expect that the total number of rows of this join, after doing the join, would be the same as the number of rows of elevation.
Okay,
Right.
that makes sense. That makes sense.
If you do that ST join and you have like, I don't know, a different number that is widely different, like sometimes I have like double the number of rows or something even more than that, then something is not working, right? The immediate step I would do is maybe try to plot that whatever you created on this object, use like map view to plot it, because then you can zoom in, zoom out, and it's a little bit
To
easier.
plot like after I join it, you're saying? Use or-
Yeah, so after joining, if you're, well, I guess you would plot regardless if you got it right or not, but especially if you got it wrong for you, or not you, but if the function like is not doing what you expected, if you plot, it's gonna be easier maybe to see what is going on, right? And map view allows you to zoom in and zoom out, which also helps with that. So I would plot that, or make a map of that with map view and try to understand what's going on. Like, why do I have so many more rows than what I was expecting? If you do end up with the number of rows that you were expecting, then I guess it still plots just to make sure that things are looking right. But then it should be good.
Okay, so
One thing, so let's see, I think you're,
cause it just, the objective this week just says to get the data from the soil data, and that's, so I don't really know exactly what you want to do.
so yeah, I guess
'Cause you gave me,
getting the data, I already did that part. So what I want for you to work on is more making sure that they match in space, because then we want to use them to kind of like what we're doing in class as well, where they have to match the resolution and the extent as well.
so do I need to just, what's my output?
So our output's gonna be, you're gonna have your, whichever way you decide to go, if you want to make your elevation coarser or soils finer.
So just do it with elevation and don't do it with like all the terrain.
Well, I mean, if you, for right now, you just need one of them, because that's gonna be kind of like the cookie cutter that you're gonna use to match with the, well, I guess that depends as well. If you wanna bring the soils to the resolution of elevation, then you just need a cookie cutter from the elevation side. So just elevation would be enough. But if your goal is to bring everything to the resolution of soils, then you have to bring the others as well.
Right, I'm just gonna, it'd be better to do the soils to the elevation.
Yeah, I think so. So you bring in elevation, you do an ST join between elevation and soils and see how that looks. And if that is giving you the end product of that is what you would expect.
Got you yesterday too. I'm going, I'm John.
Yeah, I got that. All right, so let's continue with our exercise here. So now that we have our unsmooth zones, we have the concept of the focal window. We just created this grid again, because we're gonna need to do that in the next step here, which is basically gonna be this whole next chunk here. It has a whole bunch of comments because we're gonna be doing a lot of steps in between it or within it. And the end result here would be a smooth version of the clusters. So we're gonna take our time to go through this because there's gonna be a few steps, but in the end, this zone S object is gonna be the smooth version of your clusters, of our management zones. We're gonna need these two packages as well. So stars extra and gstat. For sure, you already have gstat because that's the one that we use for IDW. I don't remember if I asked you to install stars extra before. So if you try to load that and it says you don't have it, all you need to do is just uninstall the packages with the name of that package there. Okay, so if we start off here, let's give the assignment symbol to zone S. The first thing we want to give it is the data frame we're going to be using, which is the zone underscore DF. So the one that we just created above, right? Just to remind you, zone DF, which I'm just printing down here, is the one that has the standardized field variables, has a geometry, and also has the cluster ID as a factor. So just to simplify things a little bit, we're gonna be smoothing the cluster variable. And because of that, I do want to keep just that column here to make things a little bit more straightforward. So let's just give it a pipe and call a dplyr select. And I just want to select the cluster. If you run this at this point, that's all we're doing. So if you print zone S, it's going to be the same number of rows. It's going to have the cluster column and the geometry column as well. Okay, so what we have to do here in a series of steps to get things right, to be able to apply the focal window, one of those steps is going to be to transform what right now our zone DF, imagine that each one of those cells is a small polygon, right? What I need to do in this next step here is to transform that to a point type of geometry. So right now, if we print zone S, and if you come on the first panel here, it is geometry type polygon, as we already saw on the map, right? When we made the map, these are very tiny polygons, 10 by 10 meter polygons. So I want to, for us to be able to do the focal window, we have to transform that to point. So we're going to use this function here called, get this right, st underscore cast. So this is a function from the SF package that basically is one of the ways you can change a geometry from one type to another one. So we're going to cast this geometry here to a type point. So that's how we would do it. If we just run it at this point and we print zone S, now it is a geometry of type point. Now, the next step here is where we're going to, so the reason why we're transforming this to point is because the focal window function we need to calculate some distances for that focal window to work. And those distances can only be calculated if we have points rather than polygons. So that's why we're changing that first. And now we need to change this geometry from points to XY, which again is just a step to get the focal window to work. So if you just add a pipe and you come after the next comment there, the function that we want to call here is st underscore sfc 2xy. It's really just a short name to say that you're transforming something from sfc, which is an sf type, to an xy type. If you run this and you print what zone S looks like now, it has become a stars object. And it just, it has XY distances now instead of just being an SF object. So again, this is just, you know, it's just what we have to do to be able to get the focal window to work. If you, the way that a lot of times I'm giving you things that I already figured out how to do. If you were trying to do this on your own from scratch, there's just a lot of Googling involved, right? How to do this with that and so on. And you start running into different things, and then you start developing your code in a way that it works to do what you want to do. This is one of them. It's like, there's not a lot of explanation of why we're doing these steps, other than are the steps we need to get to have the focal window to work. So I just wanted to let you know, I did not have all this in my head before I started working. I did a lot of Googling to get to this point and to figure out these steps. Okay, so now this next step here, we're just gonna give a pipe, and we're going to call a st underscore s underscore stars. So there is a difference between stopping at that stsfc 2xy and then actually transforming into a stars would be the immediate next step of that. So if we run that just to check the results, it still looks like what it was before. But at least when I developed this code here, this step of transforming to stars was needed. Okay, so now we have our stars object. This is where we can apply our focal filter. This is going to be the immediate next step. So if you add a pipe here and you come after that comment, if you wanted to stay organized with what we're doing, we're going to use a function called focal2. So this function is coming from the stars extra package that we just loaded above. It has a few arguments we want to change. The first one of them is called W. So W is basically where you set up the matrix that you want to apply as your focal filter. Because of that, we're going to use the function called matrix, because we're actually going to provide it a matrix. So we're going to give here the dimensions of this matrix, which is going to be 1, 5, 5. I don't want you to run the whole thing yet, but if I just run matrix 155, so you see what that is, this is just a way in R for you to create a matrix. If I just print that so we can look at it, this is how it looks like. So it has 5 columns, 5 rows, and then we're just filling all of them with number 1s. So that's what that function is doing for us. It's creating a matrix of 5 by 5, and we're just filling them with number 1. For example, if I wanted a 3 by 3 matrix, I would basically just change that right here. So if I run this instead, I get a 3 row by 3 column matrix, where again, I have a cell in the center. I want to make this point again. So every time your matrix has odd numbers, so 3, 5, 7, 9, and so on, you will always have a center cell, which is what we need. We need to have a center cell because that center cell is what we are changing as the window is moving. I want to show you, so the 2 by 2, if we use an even number, so 2 by 2 here, I do not have a center cell, right? The same thing for any even number, you're not going to have. Let's try 4 by 4. I don't have a center cell, right? So it has to be an odd number of the matrix, so you get a center cell, which is the one that the filter is applied to. All right, so if you get outside of that matrix, parentheses there, give it a comma, let's break line here. It has a second argument for fun. Fun means function. This is what function you're going to apply. You're going to extract from that focal window. So here I want to call the mean function. but it could have been a different function, right? So let's say on the example we saw first, it was the minimum. It could have been the maximum, whatever makes sense for your application. In our case, I want to get the mean. And we'll tell you in a second here, talk more about why that is the case. And then I want to say here, na.rm. So I want to remove NAs. So na.rm equals to true. This is the end of this part of setting up the focal function to be applied to our data set. So let's just run that and print what Zone S looks like. So now Zone S has this number. So because, and well, let me make this point as well. Because we started off with cluster here, that is the only column that we have that can be applied, can receive the focal function, because it's the only thing we have in this data set. So here what we see is our minimum is starting at 1, our maximum is 2, and then we have, you know, the median and mean values here. So really what this is doing is setting up that window, and it has a cell in the middle that is going to be, I mean, all of these cells are going to be either 1 or 2. It's basically looking at all the neighboring cells, taking the average of those neighboring cells and assigning that center cell that average. And that average is going to be somewhere between 1 or 2, because those are the 2 values that we have here. So that's what this just did for us. The next step here is I want to transform this back from raster to vector so we can more easily see this data. So let's add a pipe. We're going to call st_s_sf to bring this back to SF. We run that and we print it. Now we have a geometry type polygon, 4,381 cells. So more cells than what we started off. We'll see what's happening here once we get to once we plot this. And then just a few of them here. So you see that the first 9 are number 1, and then the 10th cell that we're seeing here is 1.14. Before we did not have broken numbers, right? We had either 1 or 2. Now these numbers can be like a fraction as well, because we're taking the mean of, in this case, 25 or 24 cells and assigning that to the center one. So I'm just thinking here, let's make a quick plot of what this looks like right now. And it's not the end, but I do want to show you why we're doing the next step before we do it without a reason, I guess. So if you run it until this point, so it's stopping at that transforming from raster back to vector, let's plot this and see how this object Zone S looks like. So I left you here most of the code for that. So we're starting with that object Zone S. We're plugging that into a ggplot, and then we need still to fill in this blank here to add the Zone S as a geom, and then we have the geom for the boundary, changing the color scale to be colorblind safe, given a new title, using the theme map, changing the title color as well, like we did before. But let's talk about here. So what is the function I'm missing here if I want to show Zone S as a geom? Geom SF, right? So right now, Zone S is an SF object. So we need to call geom SF. I want to say here, so I just want to print Zone S very quickly. It has this column still called cluster. So let's fill the map. So let's do AES and say fill equals to cluster. And then I just want to go ahead and say color equals to NA. And then add a plus at the end of that so it connects. So if we, oh, it did not work. Continuous value. Okay. So let me just, so it did not work because right now cluster is numeric. And I'm asking for scale fill colorblind. So let's just, I guess, comment off for now, this scale fill colorblind and run that. So this is how our smooth map is looking like right now. Are you all seeing the values kind of even going beyond your boundary as well? Okay, so last year, I don't think this was the case, and I don't know now why that difference is. But so just to tell you what was last year and how we fixed it. So we had basically the NA values around here. So the values did not go all the way to the boundary. So we basically interpolated those values to fill in all the way to the boundary. That was the next step that I had in my code. Doesn't seem like we need to do that this year for some reason. So yeah, I guess we can just skip that step then. And not even work on that. Okay, so we're skipping the interpolation to fill the boundary. And if we would have done that, at this point, it would have been a stars object that we had to transform back to SF. So we can skip those two next comments there. So, well, I guess don't forget to add the pipe right after that STS SF, even though we're skipping a couple of comments here, but come after the rounding one. So we wanted to connect to make it through when we do the rounding. So here's what is happening. So we have clusters 1 and 2. Imagine that you have that window of 5 by 5 where it looks at a pixel in the middle. So let's say again that you have a mixture of neighboring pixels that has both 1 and 2. So if we look at this, let me bring this map up so we can see. Let's say you're right here, right? So any pixel in the middle here is going to have a mixture of those clusters 1 and 2 around it. So what the window is setting up is going to look, so 5 by 5 gives you 25 cells. The one in the middle is the one we're changing. So we're looking at the 24 neighboring cells, taking the mean of them and assigning that mean to the pixel in the middle. That's what this function focal2 is doing for us. Now, because it's doing a mean and the current values are either 1 or 2, it means that the mean it's assigning to that center pixel is going to be somewhere between 1 and 2. So one way that we can decide we're still in the end, we still want to have all these clusters named either 1 or 2. I don't care for a fraction at that point, but I do want this to have been smoothed out. So the way that at least I approach this problem is to look at that value and just round it. So if the mean that's been assigned to the pixel in the middle is less than 1.5, that pixel in the middle after I round it is going to become 1. If the mean was greater than 1.5, it's going to round up to 2. So it's going to become 2. So right now, these values that we have on zone S, like for example here, this number would have, if we round it, it's going to be rounded down to 1. And that way we're not having broken numbers like this. We actually go back to having either 1 or 2, but a decision is based on whether that mean was greater or lower than a given threshold, which for rounding is 1.5 in this case. So that's what we want to do in this next step here. So again, make sure you add the pipe right after there. Come on this rounding part here. We want to do a mutate. So I want to call this cluster again. And we're going to use the function round, where we just give the current name of the column, which is cluster, and I just want to round to 0. So that's going to turn that 1.14 go back to being 1. And if something was 1.6, it was going to go to 2. And after we round this, we're going to end up, again, either with a value of 1 or 2 for each one of the cells. And then I want to transform that to a factor. So I want to bring it back to being a factor and not a numerical, which if you just add a pipe is going to be what we do in this last part of the code here. So let's call a mutate. I want to call this cluster underscore F to mean that it was the factor one. And then let's use the function factor that we just saw and call the current name of the column, which is cluster. So we are taking the current column cluster, applying that to be a factor or categorical, and assigning that to a new column. So not overriding the column cluster, but creating a new one. So if you run all that and you print it, now we have two columns. One is cluster, one is cluster F, where cluster is numerical, cluster F is categorical, and they are not broken numbers anymore. Okay, so now let's make this final plot here and make sure that things work. So a couple of changes on the code that we did just a moment ago was you want to allow your scale fill colorblind to be applied. On the fill here, make sure you do cluster underscore F, which is the factor version of that. And I think everything else should work. Okay, so this is what we end up having. Right, so as you can see, it smoothed out our the speckling that we had. We still have these intrusions, I guess, or I don't know if that's the best word to describe this, but we still have some small parts of one cluster inside of the other, but I guess they were large enough on the original unsmoothed version that even after smoothing, they were still there. But so this is how this is that smooth version. So if you compare what we had before with what we have now, there's a lot less noise, right? We smooth it again. All right. Also make sure that you run the dgsave. So we export this smooth version to file as well. This is going to be part of a assignment that you're going to have to bring in these layers here. One thing I want you to notice is that the title here, I changed that to be smooth zones, the size of the window, and the function. And that is also reflected on the name here of the file that we're exporting. This is going to be important when you do the assignment because you're going to have to change some things, including those two. All right. So at this point now, I want to validate our clusters. To do that, we're going to have to bring, so right now, the object we're working with is called Zone S, right? That was the latest one we have. Right now, Zone S only has the cluster as numerical, the cluster as a factor, and it has been already smoothed, but it does not have any of the field variables that we used to create these clusters, right? So I do want to bring back those variables to the same data set where we have the cluster underscore F, so we can do some validation of understanding how those variables are different for different clusters. Very similar to what we did already with the spatial temporal stability classes. So if you come here on the next chunk, I'm going to call this object zone underscore S underscore DF. So let's give it the assignment symbol. We're going to start, let me think about it. So in my code, I have starting with zone S, but the problem is that now zone S has more rows, right? So if you think about it, in my case, in your case, it must be maybe a similar situation, but just different numbers. So zone S has 4,381 rows, whereas my original data set had less than that, at 4,042, I think. So whenever we did this, perhaps it's because we did the NA remove equals to true. I think maybe that on the focal window. But anyways, if we look at this plot here, we have cells going outside of the boundary. Maybe that's what it has the extra rows. I'm pretty sure that would be it. Let me think for a moment here. I think it's one difference from last year. I guess there are a couple of things we could do. One of them is to start off with the all V and have that as our end. Doug, I think this is kind of to some extent applies to what you're gonna find in your exercise. So right now, Zone S has 4,381 rows. We want to join that with the field variables before we standardized, right? So we standardized them for the k-means, but now I want to validate with the actual numbers. So that is under this object called all_v before we standardize. This object has 4,046 rows, right? So it has less rows than that. But really, I want this all V to be our cookie cutter, because that is the one that has the actual number of rows that makes sense for us to look at. So maybe let me change a little bit of my code here. Let's start off with all V. So that is the thing on the left, and we join coming from the right with the zone S. I think that's going to be a solution here. All right, so if you remember, we've been using this function stjoin. So let's call that function here. Here we give the name of the data frame we want to join, which in our case is zone_s. We need to change a few arguments. So first, the join type. So the argument join is going to be equals to this name of the function, which is called st_equals. As you type that, make sure you do not leave the parentheses there. Just want the name of the function. And then we want to say left equals to true. So it does a left join. Let's go ahead and run this and see if it gives us at least a number of rows that would be, close to what we would expect. Okay, so we have 4,046 rows. Perfect. And again, the reason for that is because we had all V first. If we have had zone S first and then all V inside of the ST join, it would have been a different number of rows. So that makes a difference of which one you give first, which one is on the left, and then when you merge it. Yeah, I think if we'd say left equals to false, which basically means doing a right join, which the one on the right is the zone S, I think this would, I think zone SDF, so the output of this would have the same number of rows as zone S. Let's try that.
But if you had zone S, where all V is, all V were zone S.
All right, so very interestingly, when I did left equals to false, you did not return any rows, and I'm not sure why. So let's try. So what Doug is saying, what if we have, and I guess I'm bringing this up because on my original code from last year where we did interpolate, I was doing zone S first and then ST joins, and then this is what I was doing last year. And this worked last year. My gosh, this is what I need. All right. So if we were to do this, I would expect zone SDF to have the same number of rows as zone S, which is 4,300 something. So let's do that and check. Yeah. So if you're doing a left join, whatever is the data set you want to have as your frame to merge the other one, that one should come first before the ST join. So in our case here, I want to have all V coming first, and then zone S coming inside of the ST join, because then we're basically excluding all those rows that zone S has that go beyond the boundary here. Yeah, so sorry, if you are playing along with me here, changing things, make sure that you have all V first and then zone S inside of ST join. So when you run that and we check, always check when you do joins, always check the number of rows if they match what you would be expecting. So we see here 4,046, which in my case is how many rows I have in all V, which makes sense, right? For what I've been doing until this point. Let's see. And then, so here we have all the standardized EO variables, mean pixel, SC pixel, CV pixel, ST class, elevation slope aspect, flow direction, ECA, geometry, and then the cluster columns, right? And we have NAs here on the cluster columns. Seems like we have a lot of NAs. Let me do a summary here and make sure these are not all NAs, because if they are all NAs, then something went wrong. Yeah, they are all NAs. So something went wrong here. Let me try to troubleshoot. I think this is it's a good exercise. So I made some adaptations on the go here based on what I had in my code and what we had done last year. And so right now, I'm not sure why we have all those NAs there, but we definitely need to fix it. And this is not something that happened last year. So I'll try to walk you through how I would troubleshoot this, and hopefully we'll be able to find out what's going on. So the first thing I was gonna check is to see if zone S actually had the same CRS. So if it was projected, it was. All V should also be projected. It is, so that should not be the problem. Okay, I think I know what is going on. So here we skipped. Sorry, go ahead, Niva. So if you comment this part, it works. Yeah, so what I was gonna say that I think happened is when I changed the join to ST equals, if you remember, the reason why we changed it for that was because all these cells were right on top of each other, right? So we use ST equals instead of allowing the default ST intersects. And for some reason, I believe is probably because now we have a different number of rows on each one of them. Is not being able to match ST equals. And I think that's what's going on. So for now, this is, thanks Niva for the tip, because I think what I was gonna suggest we did was something a little more complex, which was actually gonna be to do the interpolation, which is based on the same grid as we use for everything else, which would have fixed it without having to change, without using a different join. So still using ST equals would work if we went back to the code and did the interpolation that we skipped today. But for now, this works. I guess let's keep moving with this fix. And if we get to some point here when we're mapping and understanding things, if it's not matching, then we'll have to come back and rethink it. Oh, okay, but so here, yeah, I think we're gonna have to do what I was proposing, because one thing is, remember that every time we do a join, we want to check the number of rows, right? So this would have been the fix if the zone SDF had the same number of rows as all V. I just printed here zone SDF and it has 16,000 rows. So even though it worked, but it's doing something that should not have been doing, right? So I guess let's resort back to what I was just saying, and kind of like, even though we don't have the reason to really interpolate because our map is already outside of the boundary, which did not happen last year. Let's still interpolate, because then we at least make sure the grid is the same. So if you come back here to the chunk, so this chunk here that is called smoothing as raster. If you remember, we skipped the interpolating steps because they were not necessary in this case. Let's go ahead and do them, because I think that's gonna fix this problem. All right, so on this interpolation step here, if you remember, this was an exam question. To interpolate, at least doing the way that we've been doing, we need two functions, right? The first one is gstat, the second one is predict. So let's call gstat here. If you remember, it has this argument called formula, where we're just gonna say cluster tilde 1 is the formula we want to apply, because up until this point of the pipe flow, we had not rounded that yet, and we had not transformed to a factor yet. So it's still a numerical, just a numerical value there. And then we also need to call, it has an argument for data, So we just need to say data equals dot. This is equals to dots because it is in a pipe flow, so we're just placing everything that's coming from above this pipe, using the dot as a placeholder in this case. So this, if we run up until here and do not add a pipe yet, just stop at gstat and we print zone S, it's just that formula object that we get out of gstat. So now, if you add a pipe, we're going to predict, right? So we're gonna call the function predict that we've been using and just give it the grid. So the grid underscore R is the one that we created a couple of chunks above. So if we do this, this is the actual step where it's going to interpolate for us. And if we just print zone S, if you remember, the output of the interpolation is always gonna be a raster. Right, so this is a stars object with the interpolated values. Where the column here, at least on my side, I think, is everyone seeing a var1 pred as the name of that column? Because I think this may have been a difference. Okay. So the interpolated values are under this column here called var1 pred. So just, we just want to keep that in mind as we keep moving here. So after doing this prediction of the interpolation, we want to turn this back into a stars object. I'm sorry, not stars, an SF object. So back to vector. So add a pipe, come after that comment. We're going to call this function st underscore s underscore sf. So before you add a pipe, if we just run until this point and we're printed, we're back to 4,046 rows. So I think this is probably what was going to fix the issue we're having down there, because now they're going to match again. Where we have one column called var1 pred, right? And this is going to be a difference we have to adapt on the code that we already developed. So as you come here back to the code, right after that STSSF that you just typed, and you connect that to the rounding function. Now here we don't have, so we're creating on that mutate, we're creating a column for cluster. We're rounding the current cluster column, but now we don't have a cluster column anymore because after interpolating, that has become var1.pred. So here you have to say var1.pred. That's what we're rounding. And then and then everything else should work. So if you just let all that run, it gave me a warning, but warnings are okay. It did not give me an error. So it should have worked. So now if we print zone S, 4,046 rows, wait. Oh yeah, so it still has var1 pred, var1 var, but it also has here cluster F, which is what we need. Okay, let me just take a quick moment here and check if everyone else was able to do this. Okay. So, and also something interesting I want to point out is we did an interpolation on the fly here, right? And this is something that in class, when I'm teaching you all these concepts, we do these in separate chunks, like very slowly, so we understand what's going on each step. Here, we're doing that right through the pipe, right? We're not even assigning that to their own object. It's just coming in, going out, and keeping it in the flow of the pipe. So just to, as you start developing your own analysis for your projects, some of the things that I've been showing you step by step, you may start combining them into pipes to, make it a little bit more straightforward. Okay, so with that, we want to create again this map here because that's going to look different. Yeah. So as you can see now, we do not have those extra values going outside of I did not change anything in the code itself. I just reran the map code. You just want to rerun that and also make sure you export with ggsave. But basically now we don't have those extra cells going beyond the boundary here. All right, so now coming back to our zone SDF chunk, if you had commented the join, then remove the hashtag, let it actually go through. And in this case, I think it should not matter at this point. Because so now all V, if I just print all V, it has 4046 in my side. If I print zone S, it has 4046 as well. So right now, the order here should not really matter because they're matching, right? So if you just run that, I would expect zone SDF to have 4046, which it does. So always check the number of rows after a join and check if that is matching with what you would expect to happen. Okay, so back on track. Now let's just get a summary here and take a look at these, very quick look at these columns. So we have all of the standardized yield, the mean pixel, standard deviation, coefficient of variation, the ST class, and then elevation, slope, aspect, full direction, ECA shallow and deep, and then we have var1 pred, var1 var, cluster, and then cluster F. So those are all everything that we needed to make this work. One thing here, I left you the code for what we're going to do next. However, I think that for this code to properly work, we're going to have to remove some of those variables from the data set, which let me look back into my code here and see what I was doing. Okay, so if we just come back up to the code, to the chunk that we did zone SDF, we're going to apply a select here to just, I guess, remove some of the columns that are not going to be used afterwards and just clean things up a little. So add a pipe. Let's call a dplyr select. So I want to remove flow there since that was not used for the k-means algorithm. I want to remove aspect. I also want to remove the var1 pred and var1 var. So minus var1.pred minus var1.var. I think those are the names. Let me just print again zone S to double check. Yeah, var1.pred, var1.var. So if we do that, let me just check again what columns we have here. And also, I think we can remove the cluster as numerical. We can just keep the cluster F as that is our interest. So let's just go ahead and do a minus cluster as well. All right, so just removing some variables out. If we print zone SDF now, so same number of rows as we've been having, at least on my side, 4046, and then 13 rows is what you should have here after removing all those variables. All right, so now if you come to the next chunk, again, I believe I left you everything here. So if you just run that, let's see if that goes through. Yeah, okay. So what this is doing for us is a little bit of a simplified way of what we did with the ST class validation on the previous exercise, which we're just creating these box plots with all the data for each one of the clusters. And it's just comparing the mean of those clusters for each one of the variables of ECA 90 or 30, 90, elevation, and slope, which were the variables that we used for the k-means clustering algorithm. And then it's adding here a p-value to note if the means are different or not. So it's not adding letters, but because we just have two groups, if this p-value is less than 0.05, which all of them are, then those two means are statistically different. Okay, so if we see here, for example, for ECA 30, and well, if we just focus on this first one here, we see that cluster 2, in my case, in your case, maybe flipped. In my case, cluster 2 has significantly higher shallow EC, higher deep EC, higher elevation, and also higher slope. So, this is just a question for us to kind of think about, but so based on these plots and what we established on the last exercise, when we were talking about high and low stable classes, which cluster do you think that would be the higher yielding and why? So we can just, let me see here if I can pull up that easily for us to look at one of those scripts. You don't have to do this on your side. I just want to do so we can look at that map again, not map, but at that plot where we had the box plots and the ladder separation. Okay, so maybe if I out. All right, so based on what we found last time, at least these are the plots that I found on my side. If we compare that to, let me pop this out as well. Make it a little bit easier to compare. All right, so if you remember here, let's just kind of look at the high stable perhaps. So high stable had high elevation. He had one of the lowest slopes. We did not include aspect in this case. It also had intermediate ECA shallow and high ECA deep. So based on that, and at least based on the clusters you see on my screen, which again may be flipped on your screen because of k-means, but if you look at the ones on my screen, which one of these clusters, one or two, do you think would be, if we had to classify them between high yielding and low yielding, which one do you think would be high yielding? Which one do you think would be low yielding? Let me ask someone online. Let's see. Dalton, what do you think?
I think it'd be number two would probably be high yield, and it's kind of got some of the same features as the high yielding one on our original.
Yes, I agree. Of course, if we think about it when we created the cluster, well, not cluster, but the groups based on EO data only, we had 4 classes. And now with our clusters here, k-means suggested 2. So there's a difference there, meaning that on the k-means zones, there's mix of what before was 4 groups on the ST class basis was 4 groups. Now we only have 2. So we're going to have mix on the zones that we just created, right? However, as Dalton was saying, we do see here that our high stable also had high elevation. It also had a high deep EC. On the shallow EC, it was intermediate, but it was still towards the higher end of that intermediate right here. The only one that perhaps is more different is the slope, where for slope, our high stable had the lowest slope, and here cluster number 2 has higher slope than number 1. So maybe that's the only one that would not match perfectly, but still, we're creating this intuition here of the management zones that we created, and I guess this is a great point for us to just stop for a moment and understand the difference here. What you see on the right, we could treat those as management zones if we wanted, so that the stability, spatial temporal stability classes, those were based completely out of EO data. They have no terrain or EC data that went into the formation of those classes, right? Those were solely based on EO data stability across 3 years, if you remember. I am showing you here these plots because we're just validating them. So we can validate them with the field data, but the field data did not impact, at least not directly, how these classes here were generated. What we're seeing then on the left side is a different approach where we are basically, at least until this point, ignoring yield. We're just saying, let's look at all this spatial variability of, EC at 2 depths, elevation and slope, and see if we find commonalities and groups within those field variables. So at that level, we are completely ignoring yield yet. So we're going to validate them with yield data, but by this point, we have 2 zones that were solely based on field data that did not include yield. So these are 2 approaches, I guess, for creating zones, and there's really many other variables that we can think about here, right? So one thing we can think of is, can we run a k-means where we include yield data as well? Yes, we can do that, and maybe you're gonna get different results. Or maybe, so I guess what I'm trying to say is there are different ways of creating zones of different types. And I'm showing you here 2 approaches where one of them is starting with the, I guess on this side, starting with the yield data and then validating them with the field data. On the other side is starting with the field data and then validating with the yield data as well. So 2 different approaches and starting at 2 different ends of that equation. We're going to see how they relate as we get to the end here. All right, I think this is a good stopping point for today. So next class, what we're gonna do, what's going on here? Yeah, for some reason my script has something going on there. Let's see if I can get this away. Anyways, next class, we're going to actually validate those clusters with the EO data and understand how they're related, and then export this to file. And I'll have an assignment for you that I will give on Friday, just so you're aware of that. All right, that's all I had. Let me take your attendance here before you all leave. All right, I just opened that issue. Make sure to claim your attendance, and I'll see you on Friday.